All right, so chapter 2 and 3 are really similar to one another. Chapter 2 is an introduction to the atom. We already finished that in one day, believe it or not. The sapling's a lot shorter than chapter 1 sapling, simply because there's not much material in chapter 2. The key takeaway from chapter 1 was the definition of an atom. We know that it's the building block of matter. It can't be split into smaller things. And then we went through all the scientific laws, so mass conservation, the law of definite proportions. We went through atomic theory, and then we talked a little bit about the periodic table, right? We're going to go back to the periodic table more in chapter 3, though. So chapter 3 gets into this idea of the atom in a lot more detail. And in order to talk about it, we kind of have to know the history of the discovery of all of the subatomic particles. So the first experiment to really elucidate what's going on in atoms was something called a cathode ray tube experiment by J.J. Thompson in 1897. So he knew about the idea of atoms being the smallest individual building blocks that make up matter, right? And his idea was, what I'm going to do is I'm basically going to accelerate them, these elements, as a beam. And then on the top, I've got a positively charged metal plate, and on the bottom, I've got a negatively charged plate. And he noticed when he pushed this ray through the tube that it actually deflected upwards. Why is it being pulled towards that positively charged plate? What do you think the ray has a charge of? It's negative, right? If we look at the beam, it's bending upwards because we know negatively charged particles are attracted towards positively charged particles. Same idea as a magnet, right? Your negative is attracted to your positive. So he ended up winning the Nobel Prize for this, even though he was somewhat incorrect, which is a little bit weird to think about. And I like this quote. It says, if in the very intense electric field of the neighborhood of the cathode, that's that positively charged plate, the molecules of gas are dissociated and split up, not into the ordinary chemical atoms, but into those primordial atoms, which we shall for brevity call corpuscles. So he's just making up things at this point. He said, and if these corpuscles are charged with electricity and projected from the cathode by the electric field, they would behave exactly like cathode rays. This sounds like gibberish, but really all he's saying is that the beam behaves like something that has a negative charge, right? The cool thing with this experiment was this was the precursor to the TV. All of the old tube TVs that you guys had, not the flat screen ones, actually use this same sort of technology where you take a beam and you actually will bend it upwards into a specific position. So what he was looking at was interesting. He knew that this must be negative. And he was also able to measure the distance at which it was deflected, right? So we would have expected it to go straight through if it were uncharged, but it deflected off a certain distance. What is that particle that gives it that negative charge? Does anybody know? Yeah. An electron, right? So prior to this, people knew of atoms, but they didn't really understand what was inside an atom. He was the first person to describe electrons. However, he was somewhat incorrect with this quote here. So ultimately what he was doing was detecting the mass to charge ratio of electrons. He didn't know the exact mass of an electron, so he couldn't tell you that much about it. He just knew it had this negatively charged property to it. That's really his takeaway, and that's why he won the Nobel Prize, was the discovery of the electron. The cool thing with this, if you ever feel irritated with your boss, was that he was incorrect and one of his students proved him wrong. So J.J. Thompson had this idea where if you look at an atom, he thought of it as a sphere, and he thought these electrons must be making up this sphere, and they must just be kind of floating around in space. That was his idea. And in order for this to be a bounce system, you can't have just negative charges. So he thought that there was just this nebulous cloud of positive charge, and then electrons were these negatively charged pieces on the inside, right? He called this the Plum pudding model. His student, Ernest Rutherford, did an experiment where he said, I really disagree with you, boss. I think you're incorrect. I think, in fact, there's a center part of the atom, and that electrons are kind of on the outside floating around. So in order to prove this, what Ernest Rutherford did was a really cool experiment. This is called the gold foil experiment, where what he did was he got a piece of instrumentation that emitted alpha particles. An alpha particle is basically a helium atom without electrons. What he did was he would fire these alpha particles at a really, 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 really thin piece of gold. Gold is interesting that way. You can take gold and you can pound it out to about 100 atoms thick. Yep.
So if they didn't know what electrons were, how did they know what an alpha particle was?
That's an interesting thing. So you can tell, so he did this experiment in 1908. J.J. Thompson discovered the electron in 1897, so it was about a decade difference. And this was also the time that they were starting to experiment with radiation. So an alpha particle is a type of radiation, and some elements will emit alpha particles. So they got a radioactive element that shot out alpha particles, and they directed those alpha particles at a really thin piece of gold. And this gold foil that they had was only about 100 atoms thick. It was very, very, very thin. Gold you can make super thick. That's why if you ever go into a fancy cathedral or a fancy building, you might see gold-plated things. It's not that they're made of 100% gold, at least most of the time. They just have a very, very thin layer of gold on top. So he fired these alpha particles at the gold, and what he noticed was that most of the alpha particles went straight through, but some of them actually got deflected in various directions. So let's take a look at this. You guys don't have to copy this down. This is just cool history. So these alpha particles matched his theory, right? Occasionally, they would run into that center part of the atom and get deflected out, meaning there was something else in the atom beyond just electrons and this nebulous idea of a positive space, right? So, does anybody know what that center part of an atom's called? Yeah. The nucleus, right? So, when we look at this model, Ernest Rutherford said there must be a nucleus, and so he called this a nuclear model. We've got the central portion, doesn't take up very much space. The majority of atoms empty space. However, occasionally these alpha particles would run into this little center portion. If it were the Plum pudding model, all of the alpha particles would just go straight through because electrons really don't occupy space. So it's a cool experiment that was used to validate his idea and prove his boss wrong. The other interesting thing was he also won the Nobel Prize. So his boss won, and then he won shortly after. So it's a neat experiment. And then last but not least, this guy called Robert Millikan did something called an oil drop experiment. If you go on and take physics here, he'll talk about it in a lot more detail. But what he did was he refined the idea of the electron, and he found the exact mass of an electron. We're not going to go into the physics of this because it gets pretty crazy pretty quick. So the key experiments were first J.J. Thompson discovering the electron, but he didn't know the mass. Ernest Rutherford shortly thereafter discovering the nucleus. And then after that, Robert Millikan discovering the exact mass of an electron. And electrons have the same mass regardless of what atom they're in, which is pretty interesting. Yep.
When was the double split experiment?
Oh, that's very different. That gets into, I'd have to look that up. But that gets into like quantum theory and wave-like behavior of particles. Yeah. Okay, so these are the cool historical tidbits. The thing that really blows my mind is if you look at the time frame here, right? We went from 1897, really having no idea what an atom was, to developing the atomic bomb in 40 years, roughly, right? So we rapidly progressed in the early 1900s with our understanding of the atom and then how to manipulate it. All right, so let's talk more about this. And this is typically the point where I start to lose people. So I've got a video for you guys. Has anybody ever seen this show? It's old. Yeah. Oh, no. Sorry, let me pull this up again. And this video does a nice job of explaining the atom in plain English.
Man, I'm asking you, Arnold.
Maybe it's because I'm dumb. Yeah, I am. Don't be telling me I'm not dumb. I'm telling you, I'm dumb.
Arnold, you're smart. You're the president of your gang.
It's different.
No, it isn't.
Yes, it is. In school, they got geometry and English and biology. And I just don't understand a thing about it, man. I just don't get any of it.
Well, what about chemistry?
That's the hardest one.
Did they teach you anything about the atom?
The atom, year after year, and I don't know the first thing about it.
I can give you the basics of the atom in 2 minutes. You'll understand it perfectly and remember it for months.
2 minutes? You crazy, you know that?
If I can teach you about the atom in 2 minutes, will you go back to school and finish out the year? How about it, huh? Come on, you're a betting man. How about it, Arnold?
Yeah. Yeah, okay, sure, you got it.
I got your word.
Yeah, you got my word. In 2 minutes.
We got a deal.
Yeah, we got a deal.
All right, sit down.
Okay.
There are 3 gangs on the street, right?
Yeah, 3 gangs.
And this right here is the territory. Now, here is the neighborhood. Got that?
Yeah.
And right in the middle of this neighborhood is a gang called the New Boys.
Yeah, the New Boys. Good name.
Okay. Out here on the outside of the neighborhood, on the edge of the neighborhood, is another gang. You know, these are real negative dudes, really negative, right?
Right.
Now, they call themselves the elected ones.
All right, the elected.
You got that? Really negative. They don't like nothing. See?
Right.
Now, they all the time out here circling around the neighborhood, just circling, you know, checking out the New Boys. Now, the New Boys see this, and they get, you know, they figure there's something wrong here, so they make a deal with another gang, a gang of very happy-go-lucky guys. They call themselves the Pros. The Pros. Now, the Pros are very positive cats. You see, they got all the good-looking women, right?
Yeah.
Right. See, now the Pros and the elected ones, interesting thing, they hate each other. So much so that they keep the same number of members in the gang, just in case you did.
Right.
So if I got 10 elected ones, how many Pros do I have?
10.
All right. Now, how many gangs do I have?
3.
Name
The New Boys, the elected ones, and the Pros.
them. All right. Who's here?
The elected ones?
All right. Now, what are they, negative?
Yeah, negative.
All right. Now, who's positive?
The Pros, and you running out of time.
All right. Now, you see right here, the Pros and the New Boys, they call their hangout the Nucleus. Yeah. Now, see, that's a real tough word. It's Latin. I kind of think it's Swahili, and it means center.
Yeah? What is it?
It's nucleus. Say it.
Nucleus. Is that really African?
Say it.
Nucleus.
You got it?
Yeah.
All right. Give you another Swahili word. It's tron. It means dude.
Yeah, Tron, dude.
All these gangs like that name so well that they all decide to use it. For instance, the Pros right here in the middle start calling themselves the Protons, and the New Boys, well, they start calling themselves the Neutrons. And out here on the edge here, the elected ones, they start calling themselves the Elected.
The electrons, the protons, and the neutrons.
Yeah. And all this right here, this is the neighborhood. This is block after block of nothing. You understand block after block of nothing, don't you?
Yeah, I know all about that. And your time is up, Professor DJ.
Good. I was finished anyway. Now you go on back to school.
School? Man, all I know about is a bunch of damn gangs that live in a round neighborhood.
Arnold, that's the atom. That's it, man. That's it. What's this right here? Huh?
Protons and neutrons.
All right, they call this the what?
Nucleus.
All right, what are these guys up here?
Electrons.
Are they negative or positive?
Negative.
And how do they move?
Round and round.
And if I got two of them, how many protons do I have?
2.
Now, protons negative or positive?
Positive.
All right, and what's all this right here?
Oh, that's the neighborhood.
Which is?
Nothing.
You got it, man. You get an A.
All right. I know that's cheesy. The key thing is with chemistry, I've found that oftentimes people make it out to be a lot harder than it is. And I would challenge you guys, if you know somebody that's never taken a chemistry course, try to explain the atom to them in 2 minutes or less, and you can use cheesy analogies like that. I've had students do that with their kids at home. You can explain this stuff to like a 3rd grader, but just do a good job of explaining it so that it doesn't sound scary, right? If you talk about alpha particles and stuff like that, you're going to lose them, trust me. All right, so let's talk about this. He said that there's 3 particles in the neighborhood, right? The first one we know was discovered by J.J. Thompson. That was our electron. What was the other one that was a counterpart to the electron? Electrons are negative. Protons. And then what was the last one? The neutrons. Whoop. Okay, and we know the charges. The electron is negative, so we'll do -1. The proton is its counterpart, so it's got to be +1. And then what about a neutron? 0, it's just hanging out there. All right, and then we've got our mass in atomic mass units. And the mass for a proton and neutron is about the same. They're approximately 1 mass unit. Is an electron going to be lighter or heavier? Lighter. They take up almost no space. And this was what was discovered in both the cathode ray experiment, the gold foil experiment, and the oil drop experiment. In fact, it's less than 1/1000th the mass. And then we've got to determine the location of each of these. Electrons are outside of the nucleus. And then we know that protons and neutrons are in the nucleus. So it's not too bad. However, we haven't really talked about neutrons very much yet. And this has to do with something called isotopes. An atom is defined by the number of protons that it has. However, an isotope is defined by the number of neutrons that it has. So isotopes are atoms or elements that differ in the number of neutrons that they have. We aren't changing the atom or element into a new element, we're just changing the number of neutrons that it has. So let's take a look at some of these examples. Let's say I've got 1 proton. I'm just going to label this with the P+. And I've got 1 electron floating around the outside. So it's kind of in this area. Let me clean this up a bit. If we look at the periodic table, what has 1 proton? Hydrogen, right? So oftentimes what we do is we use the element symbol. So I'll write H down here for hydrogen. And it's got an atomic mass of 1, meaning its nucleus only has 1 thing in it. So I'll put a 1 in the top. There are some other isotopes where you've got a proton and then a neutron. And we still have an electron out here. This is still a hydrogen atom, right? Protons define the identity. So I'll put H, and then what should be our subscript number? Or sorry, superscript. What's the atomic mass now? 2. We've got 2 particles in the nucleus. So we just say H2. And then last but not least, we've got this guy over here, where we've got 2 neutrons and a proton. Is that still hydrogen, or is it something else now? Still hydrogen. And we identified these as being different by saying this now has an atomic mass, or a mass number of 3. So protons, these guys, are present about 99.9% of the time. H2, where you've got an extra neutron, is present approximately 0.1% of the time. It's not present in a very large quantity. And then this one, I'm just going to put approximately 0. Why do you think it's approximately 0?
Because it's so unstable.
Yeah, it's super duper unstable. In fact, tritium, if you had about a milliliter in the room and you opened it up, it would kill everyone in here. So it's really, really dangerous stuff. It's very radioactive. It tends to fall apart very quickly. So this is the idea of isotopes, but the key takeaway is that these numbers in the top corner are the number of protons plus neutrons. The identity of your atom doesn't depend on the number of neutrons, it only depends on protons. Yep?
So the heavier isotope is, the more radioactive it is.
In general, if you have way more neutrons than you do protons, it tends to be unstable. And what do you think gets ejected off? If it's unstable and you've got too many neutrons, it's probably going to kick off a neutron. So oftentimes these will do weird chemistry. We're not going to get into that sort of chemistry in this course, though. All right, so let's make some notes. The first one is an atom is defined by the number of protons it has. An isotope is an atom with a specific number of neutrons. Does that make sense? Okay, so now I've got a more challenging problem for you guys. Let's look at this element, C12. All right. First thing we've got to do is identify the element itself. What does C stand for? C. So it is a carbon atom. How many protons does carbon have? 6. If we look at the periodic table over to C, right above it, there's a 6. The atomic number is the same as the number of protons. That's its atomic number. How many neutrons must it have then? 6. So just by process of elimination, 12 minus 6 is 6. How many electrons must it have? So in this case, we don't have a net charge on our molecule, so we have to balance out our protons with the electrons, right? Which means we've got to have 6 electrons too. 6 electrons. Since there is no net charge. Does that make sense? All right, so usually you'll see symbols written out like this. There are other situations where you might see them written a little differently, so I'll show you guys another example. And this one I'm going to make nice and generic. Occasionally, instead of seeing just that number in the top left-hand corner, you'll see a number in the bottom left-hand corner as well. So this is your atomic symbol. That tells you your number of protons too. Some people get lazy though, and they add this in, and this is also your atomic number. So you can include both if you want. And then up here, we said that this is your mass number, which is your number of protons plus neutrons. Does that make sense? Yep.
Is having no net charge a property of the element, or is it a property of being an isotope?
So having a charge isn't a property of an isotope. Having a charge means you've got either extra electrons or not enough electrons, and we'll talk about that in a little bit. Yeah, so if you've got too many electrons, are you going to be negative or positive? Negative. If you've got not enough, that means you're going to be positive. That's just related to whether or not you're something called a cation or an anion, but we're not quite there yet. All right, so let's take a look at some cool elements. And I want you guys to help me determine how many neutrons, protons, and electrons it has. So this is 238 Pu. So the first thing I want to know is the number of protons. Second thing I want to know is the number of neutrons. And 3 is the number of electrons. Then also, does anybody know what Pu stands for? Plutonium. So you might have to do some digging around on the periodic table to find it. Anybody want to help me with number 1? What do you think?
94.
94? Yeah, if we look at the periodic table, it's on the very, very, very bottom, kind of near the center. So it's got 94 protons. That's its atomic number. That means it's pretty easy to find. All right, how many neutrons must it have then? Yeah, so we do 238 minus 94. That gives us how many? 144? This is one weird thing about the periodic table, is typically the further down you go on the periodic table, the more neutrons can be held in the nucleus too. So it doesn't have to be an even number of protons and neutrons. All right, and then how many electrons must we have? Yeah, 94, there's no charge. Has anybody seen the movie The Martian or read about it? Or read the book? It's a pretty cool movie, right? So my favorite part about that book was he actually wrote it chapter by chapter and put it online, and then asked scientists to fact check him. And one problem that he was facing when he was writing the book was understanding how things were powered in space, right? Oftentimes, if you're in space, you can just throw up a solar panel and collect electricity. However, there are some situations where that's not enough, right? So a good example of that is the Voyager probe that was sent out in 1970. The Voyager probe is so far away from our sun right now that it can't collect any meaningful amount of sunlight. It doesn't have enough solar energy to provide the power it needs to run its computers. So this is where this element comes in. Plutonium-238 looks like this. It's a glowing red block. Nobody's heating it right now. It just sits there glowing super red hot. The reason being, it is radioactive, right? It's slowly decaying, and when it decays, it's actually releasing an enormous amount of heat. So the workaround that these NASA scientists found was they said, all right, we've got this radioactive block that's super duper warm. If we put it into a device, we can actually capture that heat energy and turn it into electrical energy. And so all of these space probes that were used by NASA, the long distance ones at least, are powered by plutonium-238. And they talk about that in The Martian. It was kind of neat. He goes out and he grabs one of the probes and he purposely tries to steal the plutonium-238 both as a power source and a heat source to keep him warm. So a little bit bizarre. The cool thing with this is a 1 kilogram block can be used to produce 500 watts of electricity. So you think about that, 2.2 pounds, you can run a computer off of this stuff, and its half-life is about, I think, over 10 years. So our Voyager probe is going to be running for decades and still will have enough energy to keep on running its computers. However, if you've been reading about the Voyager probe, every few years they have to shut down a computer because it's slowly getting weaker and weaker over time. So cool NASA tidbits if you like space stuff. The one downside with this, I'm going off on a tangent, I apologize. We're running out of it. The US currently, I think, only has less than 20 kilograms left. And so now the big debate is, well, what are we going to do when we run out? We were buying all of it from the Russians, but now the Russians won't sell us it anymore. And it was this weird byproduct of nuclear reactor chemistry that really nobody's doing anymore because we're not making that many atomic bombs anymore. So, weird stuff. Let's do practice, though. Okay, I'll give you guys an element. I want you to tell me how many protons, neutrons, electrons, its mass number, and its atomic number. So the first one is hydrogen 2. The next one I'll give you guys is 35Cl, but now I'm going to include a minus sign in the top right-hand corner. We'll talk about that. And we've got uranium 238 and cesium 137. Once you think you got it too, check with your neighbor. Yep.
Wouldn't they just be able to add protons and neutrons to make plutonium-238?
Yeah, we'll talk about that in a second. So there are some cool experiments where you can do nuclear chemistry. However, it's really, really hard.
So it would be cost effective?
It's not very cost effective, yeah. Let's do the first one together. So hydrogen 2, how many protons does it have? 1. How many neutrons? 1. So 2 minus 1 means we've got 1 neutron. How many electrons? 1. This is getting boring. Mass number? Mass number is that number in the top left-hand corner. So it's got to be 2, right? It's the number of protons plus neutrons. That's mass number. Atomic mass is the one with the decimal points. People get them flip-flopped a lot. So mass number is 2, and then atomic number we said is going to be 1. All right? Cl. What does Cl stand for? Chlorine. If we look at the periodic table, it's number 17, which means we've got to have 17 protons, right? How many neutrons does this have? 17? There. So 35 minus 17 means we have 18, right? So that's a key thing. Oftentimes students get stuck in this mindset of thinking we should have the same number of protons and neutrons. Not necessarily. All right, now the tricky part. How many electrons do we have?
More than 17.
Yeah, we've got more than 17, right? So the fact that we've got this negative charge means we have one extra electron. Electrons have a negative charge, so if you've got one extra, that means your molecule has an overall charge of a -1. You can write -1 or just negative. Negative is the same thing as -1. Yep.
Is it possible for them to have more than one extra?
Yeah, you can have -2 or -3 depending on the element. So in this case, if we have one extra electron, how many total electrons do we have? 18, right? So in this case, this accounts for one extra electron. Okay, and what's the mass number? 35. And what's the atomic number? 17. It's always going to be the same as the number of protons you have. All right, uranium-238. Anybody know what that's used for? Atomic bombs. So if you've ever gone down to Hanford, along the Columbia River, that's where the first uranium, I believe, or plutonium, I can't remember which one, it was isolated down there, and that was used in the first atomic bombs. Does anybody know the downside of this element? It's really, really radioactive. Hanford's been cleaning up that garbage forever. It is still not clean. They have these big tanks that are leaking, and they're trying to figure out what to do because oftentimes these tanks are over 50 years old. They're full of something so radioactive that you can't just send in a repairman with a patch kit. So that's a big problem right now, is cleaning up Hanford. How many protons does uranium-238 have? 92? How many neutrons? 146. So we do 238 minus 92, that's 146. How many electrons if it's not charged? 92. How many, or what's its mass number? 238. And atomic number's got to be 92 then. All right, the next interesting element, Cesium-137. Does anybody know where that's found?
Atomic bomb.
Close. Anybody hear about Fukushima, the power plant? So, yeah, it's a byproduct from reactors. Unfortunately, this stuff is super duper nasty. Fukushima accidentally released some of this into the ocean, and you can actually detect it in the water reaching the Pacific coast. So this is a really radioactive element. What's the number of protons that it has? 55. It's also found in Chernobyl, a fair amount. Neutrons? 82. Electrons? 55. Mass number? 137. And atomic number? 55. The other interesting thing with Fukushima, if you guys are interested in it, is I didn't even realize how bad it was, and I'm a chemist, right? So I was reading about it. The problem with Fukushima is the reactor got so hot when it lost power that it actually melted through its holder to the bottom of a stainless steel tank and actually burnt through a stainless steel tank. So the problem is we don't want that to burn into the air, right? We don't want to breathe that Cesium-137. So the strategy was we need to keep this cool. The easiest way to cool it down, pump water in, right? Problem is that water then becomes radioactive. We don't want that water then going out into the ocean. So they're pumping water in to cool it out. It becomes radioactive. Then they have to pump that water into a storage holding tank. Those storage holding tanks fill up, and then what do they have to do? Pump more water in, build another storage tank. So if you look at the Fukushima site, it's water tank after water tank after water tank after water tank, and we will have to do that forever until we figure out a solution to this problem. I'll get to you in a second. The other big problem is they're not able to capture all of that water and return it back to the tank, which means some of that water, for a while at least, was going out into the ocean, which is a bad idea. So the way they solved that to avoid the water reaching the ocean was they dug these pipes down hundreds of feet into the ground around the whole perimeter of the entire power plant, and then they ran coolant into each of those pipes and they froze them. basically turning it into a wall of permafrost around the entire containment facility. So Fukushima is a really, really big deal. The media has kind of stopped talking about it because, I mean, they're managing it, but that's not a good long-term solution. It's just putting more water in and pumping it out, right? So in Chernobyl, what they did was they just made a big dome and kind of encapsulated it. With Fukushima, the problem's a lot more complicated. We've been sending in robot after robot after robot to try to get an idea of what the reactor looks like, but we're cooking all of our robots. They're going in and getting fried. So now there's not only this weird permafrost barrier, but there's this trail of dead robots going to the reactor. Weird to think about, but cool chemistry. All right, so let's do some thought experiments. If you guys ever want to talk about reactors, I'd be more than happy to talk to you too. There's a lot of safe reactors. They were using a really crummy design that was very old. All right, so the first one I've got is this element that we don't know. Its mass number is 52. Its atomic number is 24. What is this element? Okay, if we go over to the periodic table and we look for 24, it is Cr. Anybody know what Cr stands for? Chromium. So it's Cr. We know it's got a mass number of 52, an atomic number of 24. Theoretically, what would happen if we just shoved an extra proton into the nucleus? It would become what? Yeah, so if we shove in one more proton, right, the mass number is going to change to 53. The atomic number is going to change to 25 because that's our number of protons. That is Mn on the table. It's manganese. It's easy to flip the two. So in this case, it would be Mn. And you're right, what charge would it have? Positive. Because we've gained a proton that has a positive charge, we would write Mn plus 1. Theoretically, we could play a thought experiment and remove a proton. What would the charge be if we removed a proton? So let's say we remove a neutron here. Or sorry, remove a proton. I'm completely flipping this. Be 23 as our atomic number. Be 51. And then we look there and we'd say, all right, that's got to be vanadium. So you can do these thought experiments. What would the charge be? Negative. If we remove a proton, we're losing a positive charge. That means it becomes negative. All right, let's do another one of these. All right, for the next one, I've got a mass number of 93, an atomic number of 38. What's the element symbol? Go over and we look at 38. SR, right? Which is strontium. It's very reactive. We'll put the 93 on top, 38 on the bottom. And then let's say we add a neutron now. So I'm going to write plus N for a neutron. Is it going to change into a new element? No. Its mass number will change. It will go up 1. Its atomic number will be 38. It will be SR. Does it have a charge? Do neutrons have a charge? No, they're neutral, so this would remain the same charge. What's the relationship between these? Yeah, they're isotopes of the same element, right? They differ in the number of electrons. All right, I think that's where we're going to stop today. On Monday, we're going to finish up Chapter 3. We're going to talk about the quantum model and then go into the periodic table a little bit more. If you guys have questions over the week,